Hi everyone, welcome to this new lecture, which is related to the electroencephalographic signal processing. One of the critical steps in the design of brain-computer interface applications based on electroencephalography is to process and analyze such signals in real time in order to identify the mental state of the user. Let me say that the signals that comes from our brain are noisy, non-stationary, very complex, and with high dimensionality. Therefore, identifying some mental state requires specific signal processing techniques and machine learning tools once you have acquired the signal. So the first step um, is related to the signal acquisition. Uh, in our case, we're going to use the emotive headset, which has a sample frequency of 120 hertz, 28 hertz. We need to acquire the signal that comes from our brain by using an electrode system. So the electrode plate system, we have the international 1020 system, which states how to configure the electrode position in order to identify the readings coming from the neurons. So the feature extraction can be done then. Why? Because you need to select some features that will be very important to identify some mental state. Let's say a mental state could be mental fatigue, or maybe if you try to imagine a movement, let's say if you're trying to imagine when you're moving your right hand, or maybe when you're moving your left hand, you're trying to imagine this. Why? Because you need to select the features then, because you need to classify them. You need to assign a class to a set of these kind of features extracted from the signal. And then this class corresponds to the mental state identified. Why we are going to classify the features in this case? Well, because sometimes the final application is not only identify the mental state. Maybe you want to control a device such as prostheses, or maybe a robot, or maybe if you're a video game gamer, let's say, you want to control the video game by using your brain. So you must identify some features and then classify them in order to detect or identify this kind of mental state. This is the process of a brain-computer interface. You need to acquire the signal, then you need to select the features, then classify them. In this kind of classification, sometimes we use machine learning tools, such support vector machines and all other neural networks and all other algorithms that you want to use or you want to compare. So in order to identify this. And probably this device control can give us a feedback for us. Let's say that you're going to design an application which could be invasive. So in this case, let's say for rehabilitation, for instance. So this will be the general process. So today's lecture will cover a feature extraction. So as an example, let us consider a motor imagery application. In this case, the two mental states that we're going to identify are imagine left hand movement on one side and imagine right hand movement on the other side. So the person is trying to think about right hand movement or left hand movement by placing the electrodes on the scalp according to the 1020 system. As I told you before, in our case, we're going to use the emotive headset for the same purpose. So in this case, once you have placed the electrodes on the scalp, then you're going to acquire the EEG signals. And then we need to interface and manipulate the signal in a digital domain. So we're going to use a computer. So this is why the name of brain computer interface comes. We need to use a computer in order to extract the features that could be very important for us to identify the mental state. So once you extract the features, so today we're going to cover this topic. Once you extract the features, then you need to classify them. Maybe using a super vector machine or neural network, as I told you before. And then once you classify them, you will probably, in a motor imagery application, you will probably have the estimated class, which could be, let's say, the left hand movement or the right hand movement. And then once you estimated the class, then probably you want to move a device, such a prosthesis, for instance, or maybe the prosthesis or an arm that or robotic arm which could be used for rehabilitation. So the extracted filtered digital signal at the end can be used as a command to control an electronic device. So, how to extract features? Well, one of the most widely used methods to analyze EEG signals is to decompose the signal. Let's say that you have acquired the signal, which is very noisy, complex, and non-stationary. And you need to decompose the signal in four different frequency bands, such delta, theta, alpha, and beta. Let's say you need to identify the power, let's say how much delta you have in the signal, how much theta you have in the signal, and alpha and beta, and so on. So in this case, this implies that the composition of the signal into frequency components. So the frequency components are the features that you're going to extract from the EEG signals in this case, and then you're going to classify them. So the power of, let's say, of each frequency band will tell you something about the mental state. We're going to cover this later. So in spectral analysis, it is common to obtain the power spectral density. Okay, in this case for the EEG signal. So before we start by defining the power spectral density, we need to know what would be the autocorrelation function. So the autocorrelation, let's say, of a real and stationary signal, let's say you have xt, which is the sequence or the data of an electrode. The autocorrelation function is defined by Rxt. Xt is just the signal, okay, the signal sequence. In this case, Rxt will be the autocorrelation function. And that will be equals to the mean function or the average between, let's say, the multiplication of xt by itself. Let's say by the same signal, but the signal, the replication of the signal is moving forward through time by tau steps, okay? So you're going to multiply both signals, which are the same, but one of them is moving toward the time domain, and then you need to average them. So the autocorrelation function will be something like this. So for instance, suppose that xt is just a square signal, which is a 0, and it has 1 over this period, okay? So if you want to make the autocorrelation for this signal, it will imply that the signal, which is x at t, is going to be multiplied by itself, but let's say that you're going to move tau steps. So let's see that probably you're going to start like this. And if you multiply both signals, let's say the blue one times the red one, it will give you 0 in this case. So the result will give you 0 at this moment. But once you move the signal, let's say x t remains static, and then you move, let's say the same signal by tau step. Let's say that you will have here at this time 0, okay? But at this time you will have, let's say at this moment, you will have a point, let's say number 1, which is, let's say this is number 1. 1 times 1 equals to 1. So at this tau step will give you 1. So let's say that again you're going to move forward, and let's say that xt, as I told you before, remains static in state position, and then the sliding function is just now here. So it becomes at the same, let's say, position has the original signal, and let's say you want to say that, okay, the multiplication for both signals will be 1 times 1 equals to 1. But remember that it means that you need to sum all the points and then average them. So at the end, you will have the previous point will equals to 1 times this another one, this tau plus 1, which is equals to, let's say, number 2, and so on. So once the function is moving forward, then the result will decrease again. So the final result of the autocorrelation function will give you this kind of triangle. Why? Because you're moving through time. Let's say this will be tau plus 3, plus 2, and so on. So the signal multiplied by itself, but moving forward through time, will give you this kind of relationship. This triangle means that at this time you will have the exact point of, let's say, the highest value of the signal. So it tells you that how similar is the signal. Let's say if you are working with network communications, you're going to detect the signal, let's say a broadband, or let's say a signal, and then if you want to detect some error in communication, then you need to multiply by itself, and then let's see if the signal corresponds to the same point. If this the highest result is not the expected value, it will tell you that probably you will have an error or a mistake in such communication. So in EEG signals is very important because the autocorrelation function will be very helpful to determine the power spectrum density in this case. So the power spectral density it's just the Fourier transform. It is just the Fourier transform of the autocorrelation function. So if you have, let's say, as I told you before, the autocorrelation function, which is tau, Rx tau, remember that it was the average between xt time itself, but let's say by tau steps. Then the power spectral density denoted as Sx in this case, Sx, let's say t, will be equals to the Fourier transform. Okay, so remember, Fourier transform is just an integral. Okay, the integral of minus infinity to infinity of the function, which is Rx tau in this case, times the complex component, which is the exponential, 2 pi I f, in this case tau, which is the steps. Remember in a previous lecture, tau, it was k, which is our denotes the steps in this case, with respect to tau in this case. So in uh, this will give you the power spectrum of the signal. So if you try to determine how what will be the power on each frequency band, it will tell you something about the mental state that you want to describe. So how to compute the power spectral density? Well, there are a lot of methods, and one of the most widely used method to do that is the Welch parallelogram or Welch method. Okay, it consists of averaging consecutive Fourier transforms of small windows of the signal. Let's say that you will have, let's say this is the original signal. This is the original signal, and then you need to determine the Fourier transform of, let's say, of small windows. So the Fourier transform will consist of, let's say, applying the Fourier transform of this segment by using a window. And let's say the window is called the Welch window. The Welch window is just like a Gaussian, let's say. It's similar like a Gaussian. So it's multiplied by them, and then it's trying to determine the Fourier transform. And then you're moving forward time. Let's say this will be time. You're moving through time, and then you're sliding the window, and probably you will have overlapping or no overlapping. It depends on the case. Sometimes you're going to use the overlap method, or maybe not overlapping. So at the end, once you average the Fourier transforms, all of the Fourier transforms, it will give you the power spectral density, so the power at the end. This is a method for, let's say, obtaining the power spectrum density. So EEG data are always time varying. So in this case, the signal is unlikely that will look like a perfect sum of pure sines. So this is the reason why you are going to use windows, let's say windows, averaging the Fourier transform by using windows, because this signal is not just the EEG data, it's not the sum of pure sine waves. It just the EEG signal is very noisy. Okay, so in this case, trying to identify the window size, let's say with smaller window size, you will have a better resolution. So in this case, it's probably you need to identify what will be the size of the window in order to identify the power, the better spectrum that you are going to use at the end. So how do we define the optimal window duration? A commonly used approach is to take a window sufficiently long to encompass at least two full cycles of the lowest frequency of interest. For instance, in EEG data, let's say that you remember that there were four frequency bands. For instance, delta, which is 1 to 4 hertz. The lowest frequency one is just 1 or maybe zero point 0.5 is sometimes in the literature tells you that 0.5 hertz is the minimum frequency uh, uh, of the delta band. So how to determine the window size? Well, in that case, you are going to choose that, as I told you before, at least 2 full cycles of the lowest frequency of interest. So it means that the duration, let's say t, t will equals to 2 times the minimum frequency. So the minimum frequency will be the 2 divided by zero point 0.5. It will give you 4 seconds. So the duration of the window will result in 4 seconds. So this window is sliding over time and then averaging the Fourier transform of this segment. Okay, so this is the method for determining the power spectrum density. So using, let's say, Python is very helpful because it has, let's say, the library that you're going to use, let's say, will give you, let's say, that will be from SciPy import signal, and then once you import signal, you can use the Welsh method. So let's say that you're going to determine the power spectrum of AF3, which is one electrode of the overall electrode system. So you need to define, let's say, an array, and then the data length and the sample frequency. As I told you before, the sample frequency of the Hemotip headset, it was 128 hertz divided by 2, because remember that the Nyquist frequency, it tells you that you need to sample twice, minimum twice the minimum frequency that you have on the signal. So 128 over 2 will give you, let's say, 60 hertz, and you're going to say that maximum frequency that you can have in your recording will give you, let's say, 60 hertz. Okay, so it's very helpful using Python to extract the power spectrum and the frequencies vectors. So by using signal.welch, and you need to pass the argument, let's say the electrode array, the frequency, the sample frequency, and this is the window size. The window size in this case, it will tell you that, well, in our previous slide, I told you that 4 seconds could be the minimum. But in that case, you can use a window size of the whole length of the recording. Okay, so you need to cover the whole sequence moving toward time. So the result will give you something like this. The vector frequency, you can plot frequency. You can plot frequency versus power spectrum density, and that will give you this the power. Let's say from 0 to 5 hertz, you have the highest power. Notice that this is the delta frequency band, and then you have, let's say, 5 to 12 hertz. This is the theta frequency band. It has a lower, let's say, power, and then alpha, it has a less lower, and then you don't have beta in that case, because this is just the reference. Oops, sorry, this is just a reference, which is 0. So it means that you have a lot of power with lower frequencies. Probably you're trying to describe that if you have, let's say, high power in delta. Delta is the slowest of the brainwaves. Delta brainwaves take place during our deepest, usually dreamless stages of sleep. Let's say delta corresponds to the frequency band resulting when you're sleeping, when you're unconscious, because the brain is not working at full. So delta, probably you will have delta when you're dreaming or when you're sleeping. Okay, so you need to identify which electrodes works with delta, with high delta, or maybe you need to identify alpha. Alpha are the default state when your mind is idle. Let's say when you're relaxed, when you close the eyes, when you're practicing yoga, or maybe you are reading. In general, when you're relaxed, alpha becomes higher than beta or theta or something like that. So you need to identify at the end, the homework will be that for each electrode, determine the power spectrum density, and then determine, let's say for this electrode, try to identify the power spectrum density, let's say for this electrode again, and identify them, and let's see in which electrodes are you notice the highest delta, the highest alpha, or the highest beta. And in this case, you need to select an experiment, let's say, for instance, motor imagery, or maybe you are going to identify the mental state of a video gamer, let's say when he's concentrating playing a video game. So if you record the brain signals for a gamer, let's see how this works. So if you record the signals for each electrode and then you determine the power spectrum density for each electrode, you will notice something very important around this. So this is all for now. These are the features that you're going to use for the next chapter. The next chapter will cover some classification methods, let's say using machine learning tools, for instance, in order to identify the mental state that you want to identify. Well, that's all for now. Thanks for watching. Thank you, everyone. Bye.